I'm trying to make this like an overview to give you an idea of what's been going on, for if you're arriving, what you need to know arriving into the area of quantum cryptography. So I want to tell you about quantum money. A talk on information-theoretic quantum crypto would not be complete without quantum key distribution. So of course, we'll cover that. Impossibility of quantum bit commitment, blind quantum computation, and if we have time, certified deletion. Okay, let me just, usually these are at the end, and you don't even have time to get there. So here are some references, and of course, it'll be much more useful when you have access to the actual slides. And there's many more references that are relevant. Okay, so let's get started. We talked about the no cloning theorem yesterday. Very, very, it's kind of like a principle, very well known. And it basically says that an arbitrary quantum state cannot be copied. It's not possible to make two perfect copies. Of course, there's no classical analogy to this because classical information can always be copied. And as cryptographers, well, okay, so the quantum no cloning theorem has been brought up as historically as a problem. It was like, okay, well, you can't copy quantum information, therefore you can't do these basic things like error correcting codes. Classically, we think of error correcting codes as adding redundance to a message. So we think of them as somehow kind of copying, like think about the parity code. So historically, people said, you can't copy, so you can't make quantum error correcting codes. That's a problem. As a cryptographer, the neat thing is that the no cloning theorem is a limitation. It's a limitation on everybody, on everything, on all of physics, including the adversary. So if the adversary is limited and can't copy, let's take advantage of that. And that's where we see these benefits of the no cloning theorem, such as in quantum money, quantum encodings, which is a broad term to kind of say you can kind of encode information into a quantum state and then get some neat properties related to that copy-protected software that we're not going to get into today. Cryptographers also have major problems because of the no cloning theorem. It means that proof techniques are no longer applicable. Those proof techniques where it's just one line in the proof, say, copy the string X and do this or do this, depending on the string X. Or maybe copy it now and later on, let's go back to that string X, just in case. Keep a backup. You can't do that in your quantum security proof. You can't keep a backup of the state where you're at in a computation. So that has caused major headaches, most of which have been resolved, but probably not all. We'll hear much more about this later this week. So things like quantum rewinding and quantum oracle queries are situations where the no cloning causes headaches. Okay, so for me, quantum information is much more like a physical object, like an apple, if you will, meaning that it has these properties that you can hold the apple, you can give the apple to somebody else, but if you give it away, you don't have the apple anymore. You can taste the apple, but that's going to leave a trace on the apple that somebody in the future can detect. And I've gotten a lot of mileage out of the apple analogy, actually. I highly recommend it. Okay, so this is what I said. Most of it, I think I've said all of this. You can taste it, it leaves a mark. You can share it. Oh yeah, you can even I can keep half of the apple and give half of the apple to somebody else, but there's only one full apple to be had. And you can't copy the apple. Okay, so conventional information, classical information, that's very different. Like in a Zoom call, everybody can see the conversation, that doesn't change it. You can share the broadcast, the stream at will, and you can copy it. These are obviously related. Okay, so getting into things that you could do with these apples. The first example I want to tell you about is also historically the first ever, as far as I know, use of quantum information in cryptography. The idea was so much ahead of its time that it took many years for it to be actually published. I'll tell you more about this, the history of that shortly. So I call this unclonable authenticity. We're going to use the unclonable property of quantum information to do something cryptographic that has to do with verifying the authenticity of a, let's say, a token. There's no message, there's no actual information. It's just the verification that something is authentic, like we do when we exchange money. We're implicitly checking that it looks like it's been generated by the authorized source. Okay, so this is a really interesting read. It's called Conjugate Coding by Stephen Wiesner, written around the late 60s. Each time I read it, I kind of discover a new nugget. It really has these really nice, let's say, ideas. If not formal proofs, there's really nice ideas, and it was really much ahead of its time in terms of, like, at that time, like, there was, of course, nobody knew about the no-cloning theorem. Nobody called these things qubits. Quantum information didn't really exist. It was really just kind of very early days. So Stephen Wiesner wrote, "The uncertainty principle imposes restrictions on the capacity of certain types of communication channels. This paper will show that in compensation for this quantum noise, quantum mechanics allows us novel forms of coding without analog in communication channels adequately described by classical physics." So see, he alludes to this uncertainty principle. We're not going to go into the uncertainty principle, although a completely different version of this lecture today would have emphasized a lot the uncertainty principle. So you can get different versions of the no cloning. Some of them would go through, like, these complementary, if you know about the uncertainty principle, is like the difficulty of, or the impossibility of observing complementary particles simultaneously, complementary properties simultaneously on a single particle. Anyways, we're not going to go into that today. We could have. We're going to emphasize more these types of coding. And as I mentioned, it was published many years later, actually in the wake of the very successful application of this conjugate coding, which was quantum key distribution. And I'll get back to that. Here's the idea of Wiesner's conjugate coding. And this is at the basis of much of current day quantum cryptography. We'll have a basis. So a basis theta represents, so we can encode a single bit, 0 or 1, into complementary bases, meaning that we can either encode it in the computational basis, either as ket0 versus ket1, or in the Hadamard basis, which is Hadamard ket0 or Hadamard ket1, which we I don't remember if we actually went through this, yesterday, so I'll just write this here for reference. Hadamard ket0 equals 0 plus 1 over square root 2, and we'll call that ket plus. And Hadamard on 1 equals 0 minus ket1. This is a ket. Over square root of 2, and we'll call this ket minus. So this is the complementary basis to the computational basis. If we know the basis of the encoding, we can also decode this as 0, and this is 1. Okay, so the idea, let me get back to where we were, is that we'll choose a random basis, we'll choose a random bit, and we'll encode that bit in that basis. So that gives you the computational bits, or the diagonal, we'll also call this the diagonal basis, ket plus and ket minus. And the idea is that if we have a single copy of B sub theta, and say you don't know what was the choice of theta and what was the choice of B. Actually, okay, never mind. If you do know the choice of beta and the choice of B, of theta and B, then you can easily verify that this ket B sub theta is unchanged. So namely, you would measure in the basis corresponding to theta, and then you should observe B. If not, you'll say that the verification failed. The intuition in terms of security is that suppose somebody does not know the choice of basis. So they will have, it could be 0, 1, it could be plus or minus, all with equal probability. And the point is that if you do not know the encoding basis, because of these non-orthogonality of ket 0 and ket plus, for instance, it would not be possible, in principle, to create two quantum states that would both pass this verification with high probability. Okay, let me just pause there to see if that makes sense to everybody. Okay, so in particular, like, there would be no way to perfectly say, oh, I'll just guess this basis, and I will measure in that basis, and then find the bit B, because that's not always going to work. Actually, this is related to one of the exercise questions that we had yesterday. Okay, so the quantum money state would be a sequence of these bits, B sub theta, for theta being an n-bit string and B being an n-bit string. Okay, so this is how Wiesner had imagined the quantum money states. You would create, he would actually do this in particles of light, which are called photons, and you can encode information into particles of light based on their polarization, which is the direction in which the particle of light is traveling. So it could be traveling like top, bottom, kind of like this vertical, horizontal, or diagonal right, diagonal left. And that gives you the 4 possibilities, ket 0, ket 1, ket plus, ket minus. So you would, the bank would mint a quantum money by generating this B sub theta. And that would be the quantum money. So even initially in this proposal, Wiesner was very much aware that technologically this is very difficult to do because, and I don't recommend investing into quantum money, because right now we don't have the technology for quantum memories, so the value of the money would almost instantaneously disappear because of the phenomenon that's called decoherence. So this is a theoretical concept, still very difficult to do. Like the world records are in milliseconds in terms of good quantum memories. Okay, okay, so that's your banknote. And oh yeah, I like this part as a tidbit from the original paper. It's the argument of why this should be secure. Okay, could there be some way of duplicating the money without learning the sequence NI? No, because if one copy can be made, so that there are 2 pieces of the money, then many copies can be made by making copies of copies. Now, given an unlimited supply of systems in the same state, that state can be determined. Thus, the sequence NI could be recovered, but this is impossible. It's actually alluding to some sort of no cloning, impossibility of knowing the underlying quantum system. You know, don't take this as an actual proof. It's an argument of why this seems to be implausible. Let's try to formalize a little bit about the security of Wiesner's quantum money. So we have the quantum money state. We have an attacker. The attacker is trying to create 2 quantum money states, both of which would be accepted if we were to verify, where the verification means to measure in the basis given by theta, and accept if you get the exact same bit string B. So the question is, how does the difficulty of cloning quantum money, we'll call this cloning if it's successful, how does that difficulty scale with the number of qubits n? And this was in the exercise set. So if you had a single qubit, one possible attack would be to guess the basis, measure in that basis, and based on that result, resend 2 qubits that correspond to this measurement. With probability 1/2, the basis will be guessed correctly, and actually you will have created 2 copies. We're talking about a single qubit at this point. And the 2 copies will be accepted. That's the easy case. If the basis is incorrect, then actually the attacker is going to create something that is in the complementary basis, and then the probability that both of these accept, it's incorrect, right? It's in the wrong basis. Each individually will accept with probability half, so 1/4 for both of them accepting. And so the total probability of acceptance is 5/8 for this simple attack. So then you can wonder, okay, well, is this the best you could do? And again, the original question, how does this scale when we have n qubits? The answer is actually we can do better. We can do 3/4. The strategy, as far as I know, doesn't have this nice explanation. So I'll just refer you to the reference for that one. The reference is this paper. And interestingly enough, this came out in 2012, so 10 years ago. And like many years after Wiesner had proposed this, did we finally settle the question of what's the exact success probability of this simple type of attack for Wiesner's quantum money. And this was done using a mathematical technique called semi-definite programming, which I'm not going to cover today. You can ask Thomas about it. He's one of the authors. And the answer is actually 3/4 to the n. So quite surprisingly, I would say, we have the optimal attack of 3/4 for a single qubit. And it turns out that if you have n of these, there's no, the best attack is actually to do this single qubit optimal attack on all n systems. So that gives you the security that you would want. So all you have to do is scale n to get the security parameter that you would like for this quantum money. It's called private key quantum money, meaning that the verification requires the description of the original preparation, right? So maybe this is better seen as something like a subway token type of thing. So you can only spend the subway token at the place that originated the token because they need to know the private key. That's a drawback of this kind of scheme. I mean, it's in the design. There has been further work. Actually, in the past 10 years, it's kind of like a revival. So the quantum money sat there for a while, and now we had more techniques, maybe simply more people interested in it. And so there's work on making this noise tolerant. So right now, the bank will almost always reject any scheme that you would actually do in practice because of noise, right? So as soon as there's a small little amount of noise, the bank will say it's not good. These authors allowed some errors, and the proof nevertheless goes through. Then we have quantum money with classical verification. So what if you would want to somehow only be able to classically interact with the bank to verify the money? That's possible. And then public key quantum money is solving this issue that now with public key quantum money, anybody can verify the money. Okay, so this is quite a new problem because you want anybody to be able to verify, yet nobody should be able to forge and create a new quantum money that will be also accepted. So this requires sophisticated techniques, and I would say that this is really an ongoing topic, public key quantum money. Okay, what do you think about quantum money? Any questions or comments? Yeah?
I have a very silly question for missing something. So if you're making computation assumptions in, like, for example, public key quantum money, can we get some analog of unclonability from computation assumptions, or is that completely ruled out for obvious reasons?
Okay, so the question is if we're willing to make computational assumptions, which indeed is the case in public key quantum money, like we can kind of, I think there's arguments to show that it's required to make computational assumptions. Then can we get a type of computational unclonability?
Yeah. Or is it obviously impossible?
I think it'd be really nice to be able to define computational unclonability. And like, what does that mean? I think now we're in, my presentation is about information-theoretic quantum crypto, and we're going to focus on that. And the rest of the week we'll combine, and Fang alluded to this already yesterday, we're going to combine more and more classical or computational assumptions mostly post-quantum computational substance, with quantum information. So that gives you a type of computational property of the quantum information. So we do see phenomena that are kind of related to unclonability in a computational sense, such as computationally secure certified deletion, which I'm probably not going to get to, but that exists. And like you can get benefits from adding the computational assumptions, yet you still get this really nice thing that you do something quantumly that's impossible classically. Does that answer a little bit? Basically, if you could define unclonability, I'd be really happy, right? You know, like what is it? And that's a little bit of my mission in life. Any further comments, questions? Okay, we talked about unclonable authenticity, verification, like verification that something is created by the authentic source. What about information? What about messages? What about communication? How could we take advantage of the no cloning principle in some sort of exchange of messages, right? Because quantum money doesn't have any underlying information in it. So this is the story is very closely related to quantum money. Actually, the story is that Gilles Brassard, who was one of my PhD supervisors, in 1979 met Charles Bennett, a physicist at IBM. In some interesting circumstances, they were actually both swimming in the ocean in San Juan, Puerto Rico. And Bennett comes up to Brassard and says, hey, I saw that you're giving a talk on cryptography later. I'm a physicist, but I know about this really cool thing related to quantum cryptography. I know about quantum money. And he explains quantum money. The story is that Charles Bennett was the roommate of, or housemate of Stephen Wiesner some years prior, and they had kept in touch, and Wiesner had told him about his manuscript on conjugate coding. Charles Bennett was really trying to bring that idea to fruition, to make it, to find further applications. And he really found the right person because even to this day, okay, this is slightly outdated, these two people are very close collaborators in the interplay between the physics and computer science. So they had not swam back to shore yet. They had actually figured out a type of encoding that would be useful. I think it was related to reusing the key in a one-time pad scheme. Just shortly thereafter, they kind of transformed that idea into what now is known as quantum key distribution, and that's what kind of became most widely known. Okay, so what does quantum key distribution do? So say you wanted to communicate with absolutely unconditional security. Well, if you're doing, if you're looking for a symmetric key encryption scheme, these things like AES, that's not going to do because there's, in principle, a way to break it with lots of computational time. So that's not unconditional. RSA or the post-quantum schemes that we've been talking about this week, they are not unconditional. They can also be broken with large amounts of computational time. So it seems like the only solution is the one-time pad that we've talked about earlier this week. And I have a pun on the one-time. I don't know if it's a pun. I don't know if it's a joke. It's a joke in French. So talking about the multiple. So Ottawa, University of Ottawa is the capital of Canada. Canada has 2 languages. University of Ottawa is the largest officially bilingual French-English university. So in that spirit, I'll tell you about le masque jetable, which is the name for the one-time pad in French. It's also what everybody is wearing right now. So actually, the pandemic has brought this masque jetable to the forefront, and also self-testing, for those of you who know about that. So I think it's really funny. Okay, so The one-time pad has actually been used in practice. It's very expensive because you need to share these long keys, and that has its own risks. It was used in this Washington-Moscow hotline. If you know who you're going to talk to ahead of time, then you need to establish the keys. The problem is that if you're looking at a network of communication, which is what we rely on nowadays for our interactions, then we need more and more shared secret keys just in case I happen to want to talk to any one of you in the room, or et cetera. So we have this complete graph of keys that are required to be established ahead of time. And there's n choose 2 possible pairs in a room of n people. Conjugate coding to the rescue. Let's use this idea of conjugate coding, sort of version that you can't copy information, to distribute these keys. And this is what's known now as BBD4 quantum key distribution. Okay, so we're going to have many versions of QKD in this talk. And the reason is that it's complicated. It's actually easy. The concept is simple. It's more and more complicated when you want to talk about the details and when you want to talk about the proof. And when I was learning this material, I didn't understand that. I was like, why are people talking about QKD in this way and in that way and in different ways? And actually, probably for different researchers, they focus on different areas of QKD because it's a bunch of pieces. So that's what I thought I could contribute, which would be to kind of explain to you that this is a broad topic. Probably in one lecture, we're not going to cover everything, and just try to take it all in. There's different approaches, different reasons people look at different areas of QKD. So, yeah. Feel free to let me know if I can explain anything better also. Okay, so this is the very, very high level of QKD. There's Alice and there's Bob. They want to share a secret. There's an eavesdropper in the middle. So classically, there's nothing they can do, right? Like Alice, if there's an eavesdropper, the eavesdropper will read all the information, and the eavesdropper will have the same information as Bob. Quantumly, let's say Alice generates a random key and puts the key in an apple. Then she sends the apple to Bob. Okay, Bob checks the apple, and then he finds the key. If there's an Eve in the middle, and Eve tries to check on the key to get some information, it's like Eve is tasting the apple, and then Bob can detect that. Okay, literally this is the very basics of QKD and the concept of why it could possibly work. Okay, so we've, yeah.
Why can't Eve give a different apple?
Oh, why can't Eve give a different apple? Great question. That would be like substituting completely different fruit, and let's say like Bob can recognize that it was the original apple. You know, like apples are actually distinguishable, right? Like I can tell. The analogy actually breaks down.
Sorry.
Yeah. Yes.
But is there Eve malicious, or she just eavesdropped?
Okay, so the question is Eve malicious, or if she just eavesdropped? Interestingly enough, quantumly, there's no difference between copying and modifying. Okay, because the operation is a control not, and the control not in the classical basis copies, but the control not in the Hadamard basis modifies. So the answer is yes, because you asked an or question. So there's actually no difference, yeah. Yeah, anything else? Yeah.
You said that Bob could distinguish whether or not the apple in this case was actually sent by Alice, whether it was a different message. Is that because they've agreed upon that beforehand, that they both had this idea that whatever's going to be sent is going to be sent in an apple versus something else?
Okay, so thanks. I think I can clarify that question about the authenticity of the apple. And maybe this is a few slides later. We'll assume that they have actually a short shared secret that can be used to verify the authenticity of the apple. So QKD is actually better explained as a key expansion scheme. Another way to see it is that if Alice and Bob don't share an initial shared secret, then there's really this person in the middle attack. Like, how does Alice even know that she's talking to Bob? And she could end up sharing a key with Eve, and everybody would be none the wiser, and she wouldn't know. Yeah. Okay, so there's these major pieces in this intuitive picture of eavesdropping by Eve, which is, let's say that's anything other than the identity. Okay, so like Eve gets, like the apple passes in front of Eve and she can let it pass, or she can try to interact with it. That's called eavesdropping. And the idea is that eavesdropping is going to create errors, modifications to the apple, and that can always be detected by Bob. And making this slightly more concrete in terms of the quantum information. Why does it say this? Oh, okay, no, never mind. So use the quantum channel to send a random key, so that's the random key idea. And actually in QKD, the key is going to come to be, it's actually not chosen ahead of time. It's like a key agreement, let's say. But that's a detail at this point. And then if Bob is satisfied with the integrity of the apple, et cetera, we'll use this one-time pad to send the message. So therefore, the problem is this key distribution or key agreement type of thing. And after that, we'll use the one-time pad. So we're not going to talk about the actual encryption. OK, so version 2. Slightly more towards actually doing this with actually quantum states. And this is some slides that were passed down originally from Philippe Gragier. Okay, we're going to use conjugate coding. And kind of like a pet peeve of mine is that these conjugate coding states, everybody calls them BBD4 states, because BBD4 used them to do quantum key distribution. But really, it's Wiesner who came up with them. So I don't know why we call them. Well, I guess there's an explanation, but really, conjugate coding or Wiesner states tells you more about the origin of these things. So Alice is going to choose an encoding basis, much like in quantum money, and a bit value. So this would be the theta in the quantum money, and this would be the B in the quantum money. So she encodes each bit, bit B according to the basis. So this is the picture of the illustration of the photon polarization, if you wish. So this is the computational basis, also called rectilinear basis, and this would be a 1. And here's another computational basis, and the other bit 0 is encoded like this, and then these are the diagonal bases, 1 encoded diagonal left and 0 encoded diagonal right. And this is what she sends over the channel. This is what Eve can possibly eavesdrop on, these quantum encodings, conjugate coding states. Okay, so Bob, if he knew the decoding basis, that would be like quantum money. He knows the decoding basis, he'd measure that basis, and he could verify. Oh, but he can't know the decoding basis. That would be like a secret, and they don't have a shared secret. They have a short shared secret, but definitely not enough to share this decoding basis. And if they had a secret, long shared secret, we would not be doing QKD. So let's get him to, like, the idea is let's get him to randomly pick a basis. He doesn't know what it is, just randomly pick one. So this is a random string of bases, and he'll measure in that basis. So for instance, if Alice sent in this encoding basis, she sent a 1, his basis coincides in this case. He will measure a 1 for sure, because these bases coincide. When the bases do not coincide, then actually his outcome is uniformly random by this complementarity of computational and diagonal bases. And then Bob sends a classical message to Alice, which is his choice of bases. So on her side, Alice now has all the information to know in which positions Bob has actually measured in the correct basis, where the bases correspond. So by some public discussion, they will eliminate, this is called sifting, the positions where the bases do not coincide. So that's why we have these parts here that are removed. All the other places is where the bases coincide. And this we'll call the sifted key, which in this perfect case where the sent qubits arrive perfectly, they're measured, and because of this discussion phase, these will all perfectly coincide with the original key bit value, the original bit value that Alice chose. Any questions about this? Yep.
So how does this help? She can't just, there's going to be a random communication, and she's going to say which bases were right and which ones were not. I mean, that random communication, she can't just tell the bases that were measured.
So how does this help? The thing is that Bob announces this after the adversary has possibly attacked. Maybe in the next slide, okay. The next slide, there's an adversary, Eve, who will be doing eavesdropping. The point is that at this stage, the basis is completely unknown. So it's okay to, well, it's okay. I mean, we'll have to work very hard to show that it's okay to publicly announce the basis theta after the fact.
So we will be able to tell whether something happened on the way.
Yeah. So this part here has an eavesdropper in the middle. For illustration purposes only, we'll assume that the eavesdropper decides to choose her own basis and measure in that basis. Okay, this is one possible attack. And you see here, the eavesdropper chose a different basis from the encoding basis. And in the measurement, the eavesdropper might observe a 0. And in the decoding basis here, this one was going to be sifted out anyways. The idea is that there are some possible errors introduced by the adversary. So let me choose the third column. So here is a diagonal encoding. The adversary chose a rectilinear measurement. So this is going to possibly introduce some noise when Bob goes to decode to measure in his diagonal basis, which happens to correspond. He'll see a 1. But Alice sent a 0. So via some next steps, they can detect with a certain probability that there are positions that do not agree. They would expect them to agree because the bases coincide. Yet they don't agree. So this is the bite in the apple, meaning that they can detect that there's been a modification. And we'll, there are a bunch of steps that will detect and possibly even compensate for small amounts of noise. Okay, yeah.
I was wondering whether it would be equally secure if Bob would tell Alice he received the states, and then Alice would just tell him what basis she used.
Yeah, thanks. So that's a version which is equally secure, where Alice sends, and then Bob says, thanks, got them.
Well, Bob has to let her know when he received the...
Yeah, let her know that he received them.
I'm wondering whether an adversary can just measure Alice's and then send her own to Bob. I'm not sure.
Yeah, okay, so let me repeat that so I can think about it at the same time. So Alice would send, Bob would say, got them, and then Alice would broadcast the choice of bases. And the question is, would that be just as secure? In principle, yeah, I don't see the problem. In practice, there's no way for Bob to know, like if you're actually building this, I don't think Bob could say I got the qubits without measuring them. Like, in an actual Paradis. Yeah, yeah. When you think about it in the actual lab.
I see. You don't know that you got it until you measure it. Yeah.
A little bit. That's kind of like the way things work right now. Yeah.
For the sifted key here, there's no guarantee on the length of correct matchings. So is it a problem if a lot of the key is disrupted and there's only like one bit that actually is sifted correct?
Okay, so thanks. So the question is, if you have lots of places here where there are errors, what the scheme is going to do is that, in principle, Eve could maximally eavesdrop. Maybe just take it all away, take the entire apple and substitute with a pear, okay? And then they're going to find lots and lots of errors, and then actually the best they could hope for is to say, sorry Alice, sorry Bob, it didn't work out today. So they're not going to share a key. So what happens is that if the error rate, which is these detected, how many errors we find, if that's too high, they're going to abort. If it's too low, they're going to squeeze out the adversary. I'm getting ahead of myself, yeah. Okay, so this I mentioned when we were asking about the authenticity of the apple, right? So actually, QKD assumes an authenticated classical communication, and this can be achieved information-theoretically with a short shared secret by some very early work on Wegman-Carter, and I think this is still the best we can do. So QKD is more accurately described as a key expansion protocol. So what are the steps to go from the sifted key to the private key? And this is still a very bird's-eye view. So how are they going to even know that there are places where the sifted key does not correspond? They will publicly compare, they'll sacrifice some of these positions, let's say half of them. So Bob will announce a random subset of half of his sifted bits, and Alice will do the same, and then they'll publicly they'll realize what is the error rate. They'll see how many positions differ. And they will abort if this error rate is too high. 11% is the usual threshold due to some calculations. And at this stage, they know that there's some, yeah?
Sir, can you elaborate on that 11%? If I understood correctly, I think if they're just talking about the measurements on the bits where they agree on the basis they're measuring, I would have thought that the theoretical maximum error rate is 0. What's the error? Like what?
Okay. So why is there an 11% maximum? Maybe this should be 99%?
Oh, okay, yeah, other way around. But, well,
it was like eavesdropping. They're trying to set that it was so to be as mistake.
I see. Okay, so if there's eavesdropping, then the theoretical maximum would be 11%.
Yes, the
I see, okay.
yeah, if there's no eavesdropping, it'll be 0.
Yeah, that's what
okay.
I
Okay, so we're looking at the scale. Okay, 0 would be no eavesdropping, and they'll all be happy and then they can actually extract a longer shared secret. With up to 11% noise, there's going to be extra steps that will maybe generate a shorter shared secret. Nevertheless, we can still guarantee that it's almost perfectly uniform and unknown to Eve. Okay, so that's what I was mentioning here. We're going to do, so we have this estimate on the error rate, and we're going to do a bunch of things to get a uniform key. And this is called information reconciliation, or maybe a more modern terminology is error correction. So we have n/2 positions remaining that have not been opened for this estimation, and for these ones, we'll do error correction to reduce the error rate from the point of view of Eve. It's all about making sure that Eve doesn't know anything about this key, the final key that is agreed upon. So there's some interactive ways to do information reconciliation via a series of parity checks, or more generally, using error correcting codes. And we'll talk about that briefly. Okay, now we've kind of reduced the error. And the final step is called privacy amplification. Eve is going to have some information about the key. And that is from this public key comparison and from the error correction. The point is that we're going to mathematically bound that information that Eve has and then apply this construction, which is called privacy amplification, to make a key that's shorter, but that achieves that amount of bits of uncertainty that Eve has. So this is done using a random hash function, and we'll go into more details. Okay, so that is still a high-level overview. Any questions? Yeah.
The second bullet point is after BB84, developments after BB84.
The second bullet point, like the information reconciliation?
From sifted key to the private key. I mean, it's error corrections though. I mean, let's take a look at
This one?
Yeah. All these things came after BB84.
All these things get? Sorry, just.
After, they were like further developments of BB84.
Oh, like thinking about the original paper and what they proposed versus, oh. I'd have to go back and read that actual BB. I don't think I've ever read it. Sometimes I wish I was doing crypto in the 80s. Because they didn't, like, there's no proofs, right? It seems like a lot easier. I don't know.
This is classical error correction, right? This is quantum.
These are, yes, this is actually all classical techniques, which, okay, error correction is just straight classical. This requires a proof against quantum adversaries. It's the same idea. Like probably BB84 had some vague ideas of how you would do this and how you would do this. Yeah. Okay. Okay, what about security? Okay, I haven't even defined the details of the protocol. Let's try to think of how we could make you prove this secure. Sometimes we attribute security to the no cloning. Okay, let's just, as a sanity check, if there were no cloning theorem, so say we could clone quantum information, then Eve could keep a backup copy of each of the quantum signals that is sent, and she'll wait for Bob to announce the basis theta, then she'll measure in that basis on her backup copy, and she'll have the exact same information as Bob. Therefore, there's no secret between Alice and Bob that Eve doesn't have, and there's no way for them to get a shared secret. So that's true. Like, if we did not have the no cloning theorem, there's no way we could prove security. Of course, this is not a proof. Okay, so the actual proofs of quantum key distribution, they appeared 15 years or later after the proposed protocol. There was a long period of time during which, like, there are lots of questions of how we might address the question of formally proving security. And there's a whole repertoire of proofs, at this point, of proofs for BB84 and versions thereof. You know, when I say BB84, this is the general idea of let's use conjugate coding to send these things. But then, of course, you know, how do you do the error correction? How do you do the privacy amplification? Those all kind of create different variants. And some of my favorite ones are via quantum error correcting codes. There's a way to kind of massage the entire QKD into a very complex quantum error correcting code and then conclude security. There are definity reductions, which are ways to reduce the security of the general attacks to security of simple attacks, single qubit attacks, actually. So it's like a symmetrization thing, and you can also get some nice proofs. There are uncertainty relations, which I alluded to at the beginning. in terms of entropy, so this is more information, so that's useful for the keys, and you have some uncertainty relations, and it's kind of like, well, the more information Eve has about the key, the more she's going to disturb the communication. You know, it's all these intuitions that actually become formal with these proof techniques. Okay, and then finally, there's the sampling proof technique, which is the one that I want to tell you about today. I just want to give you an overview. I want to give you an overview of other topics related to QKD before actually going into this proof. So we'll do that now, and then we'll go into more details of the proof. One of the reasons why QKD is so successful is that this is something that we can actually build. The scheme does not require a quantum computer, right? You didn't see any gates, you didn't see any memory. You saw preparing single qubits, sending them, and measuring them. And that is something that we can do with photons, actually particles of light, and it's been very successful because particles of light are very good at traveling. And traveling is really good for communications and if you want to secure communications. Okay, so QKD first, I mean, there are many others. We had the experimental demonstration, very kind of proof of principle thing. We had the proofs of security, came around the year 2000. First bank transfer using QKD. Then we're talking about networks, so many nodes, and then you have point-to-point different configurations within that network want to communicate privately. And then in order to increase the distance, so we're up to about 200 kilometers, and that's using fiber optic cable. In order to increase the distance, what people are doing now is talking about, and actually not just talking, actually doing it, putting sources of qubits on satellites. And then the satellites can actually have a wider reach, and they can enable the QKD between even longer distance than 200 kilometers. And I think this is outdated. You can buy these QKD commercial products. Probably the most well-known is ID Consig, originally based in Geneva. Okay, so I alluded to this practicality of BB84 being why it's so successful, and notice that Alice's technology is to prepare and send single qubits. Bob only needs to measure them, so he just receives them and measures them on a random basis. Error correction is going to be actually integrated into the protocol. We haven't gotten to this yet. We're going to, even if there's like non-malicious noise, that will be included in the analysis. Sometimes people will think, well, let's just do another layer of error correction on top of, like, we'll do this noise-free protocol and let somebody else worry about the error correction. Okay, you can do that, but then you can't build it in the lab directly. You'll have to do this extra step of your analysis for the actual errors because there's lots of errors if you're trying to actually build this in an experimental setup. Okay, so under a small amount of noise, the protocol does not abort. It's still going to work. And the noise is corrected, and the final keys agree. We also saw this phenomena in the Wiesner quantum money, right? Saying, well, perfect quantum money, it's not realistic, and people have done analysis now for a noisy quantum money. And this is called noise-tolerant single qubit prepare and measure, and it's kind of like the gold standard if you want to make a protocol and say this is feasible with current technology. And I guess, with the advent right now that we're looking at existing cloud quantum computers, maybe in the longer run, full-scale quantum computers. If you're thinking about the technology and actually building it for quantum cryptography communication protocols, this is what you should aim for. Okay, and then recent directions in QKD. Again, we'll do the proof shortly, but I want to tell you about other things related to QKD that you could have on your radar. Device independent and one-sided device independent. So right now, in my description, Alice trusts her quantum device to be sending the qubits as we said. Same thing for Bob in terms of measurement. But maybe you bought your device from a seller and you're not really sure that it's doing what you think it should be doing. So there's actually different protocols with different analyses that will that still establish security in these contexts. So I mean, they're more involved. But maybe for your next steps, if you're really interested in QKD. There's a really nice tutorial online on this topic from QCrypt. And by the way, if you're interested in quantum cryptography, QCrypt is the annual Quantum Cryptography Conference, and there's really some really nice talks that are available online, and maybe you could attend in the future. Continuous variable QKD is related to actual implementations, which are more adequately described in some other formalism. So there's an entire area of QKD related to that. And finite size key effects. So if you're actually wanting to build this, it's like what's the key rate that you can actually get, never mind the asymptotics of possibility or whatnot, and then actually how much, just how much key can we squeeze out and like increase the key rate, et cetera, to make it more and more practical. And side channel attacks, which is related to the first one. So in our proofs, we model these devices as ideal devices. And it's been shown by some people that call themselves quantum hackers that there are ways to actually interact with the quantum devices that will make them behave in ways that are not modeled in the security proof. So that's very interesting. And there's lots more. OK, any further comments or questions on QKD before we get into a more technical proof? I thought this school would not be complete with an idea of a proof of QKD. This is the most advanced topic, I would say, in quantum cryptography because it's been on the radar for so long and because it's practically feasible. So we get a lot of inspiration, like even if you're not working on QKD, from these security proofs. Okay, so the one I chose is called sampling, and originally by Bouman and Fehr in 2010, and I'm following very closely this presentation in a separate publication that kind of goes straight to the QKD application. Here they present a more general technique called sampling. We still see the technique in this version, but we're just kind of going straight for the proof of QKD. And full disclosure, I'm using a lot of the notation equations and figures from this reference. Yeah, and the reason I chose this sampling is that I thought it's the most kind of computer science type of approach, I think. That really, I think that if you're looking to extend it or whatnot, maybe this is the one that's most applicable. OK, so summary again of BB84. OK, Alice is going to prepare these conjugate coding states. This is what we've talked about before. He's going to measure on a random basis, compare, sample. The noise level might be too high, and they'll abort. Otherwise, they'll amplify the secrecy and correct the errors. And they'll get a shared secret. If there's an Eve in the middle, she can do an arbitrary, like we have no assumption on exactly what type of map she might be doing. So we can kind of see that she'd be sending a quantum state row. And importantly, keeping part of the original state for herself. And she'll send that to Bob. There is a different picture in which we can reason about the exact same protocol. And this is related to the purifications that we talked about yesterday. This is the basis of pretty much all proof techniques in quantum crypto, even beyond QKD, is we'll change the protocol prove security on the changed protocol. It's going to be easier in that model, and that will imply security on the original one. And why do we do that? The original one has some benefits: prepare and measure, single qubit, noise tolerant. The proof is going to be done in some other model that seems less realistic to implement. It's called the entanglement-based BB84. And here we see that the adversary starts. The adversary starts by sending a message. The message is in 3 systems. So this is a density matrix over A, B, and E. And she sends these registers, A to Alice, B to Bob, and she keeps the E portion. And then we're going to reason about the security, assuming that this initial row ABE is unknown. That embodies the entire attack of Eve, is in creating this state, right? So that means that in the original QKD, we see as Eve as eavesdropping on something that Alice prepared. In the one that we're going to prove, we argue that the E system is going to be independent of the key that Alice and Bob agree upon. And as a sanity check, okay, yeah, and then the protocol is actually the same, except that Alice will measure in a random basis theta as her first step. And then Bob does the same thing. As a sanity check, we can emulate the original BB84 protocol in this model by having Eve send an EPR state. So this is this maximally entangled 1/√2 ket 00 plus ket 11 in a tensor product of her reference system. If Alice chooses the basis theta equals 0, she'll be measuring in the computational basis her first qubit. And that means that Bob's system will become either ket 0 or ket 1, depending on what Alice saw. So that is equivalent to the preparation of the conjugate coding states in the computational basis. If theta is equal to 1, a quick calculation, if you do a Hadamard on the first qubit here, then you can show that Bob's state will also become a Hadamard on his qubit. So that if she measures in the Hadamard basis and sees plus, Bob will also see plus. Same thing for minus. Oh, but that's the same thing as what we originally wanted for the QKD BB84 scheme. So now we have at least one way. If Eve does this and actually sends this, we know that we'll be preparing these conjugate coding states. Of course, the general security makes no assumption on the row ABE. It turns out that if we show security for the entanglement-based scheme, that's going to apply the security of the original scheme. So from now on, this is what we're going to show, and actually all the papers that you read will kind of start by that step almost. Okay, we talked about this yesterday, the classical quantum hybrid systems. It's a notation that's convenient to describe a classical random variable and together with a quantum state. So we have this x, a classical random variable, and a probability distribution on that random variable. And then a quantum state on the E system. That is usually going to represent Eve's system. And with probability px, the system will be in this state. So that's rho E condition on x equals x. So that's how we can represent the hybrid system. Say we encode the choice of x into a quantum state. So this is a quantum state. In the computational basis, it encodes the classical message. So this is this hybrid rho xe between classical and quantum. And then sometimes we'll talk about rho x, which is to trace out the E environment on this hybrid system. And that gives you the classical random variable, but encoded in a quantum system. Very important for us will be the concept of independence. So if you can write rho xe as a tensor product of rho x tensor rho e, it means that the rho e system is independent of rho x. Because if you were to trace out remember that row X means to take this system and trace out E, and similarly, row E means to take this system and trace out row X. So this is meaning that actually there's no correlation, because when you trace out either side, nothing changes. Let mu X denote the completely mixed state. So that's the mixture of all the possible bit strings in that set. If we're talking about creating random keys, this is an important one, the mu X, because our target is going to be to create a random key, mu X, that is in tensor product with Eve's system, meaning that Eve's system is independent of the key. Okay, and so next is that we're actually not going to achieve equality. We're going to need a notion of a distance. So we want to be close to a uniform key, for instance. We want to argue that quantum states are close to each other. And this is a really fundamental definition. It's called the trace distance. I just told you that it's fundamental, but actually don't worry about what the definition is. The only important thing is the operational meaning. So the trace distance tells you for any physical process, it's a bound on the probability of the states behaving identically. Okay, so the operational meaning is more important. For any physical processing, the two states behave identically except with probability at most delta rho sigma, and we'll call delta this trace distance. For key distribution, we'll say that the scheme is secure if the trace distance is small. So what's this? So we have rho xe, and this will be the final state. X will contain the key that Alice and Bob agree upon, and E will be the reference system that Eve holds. And this is, once again, this is this uniform distribution and this tensor product idea. So this is the ideal thing that would be perfectly secure, and we're going to be able to argue that the trace distance is small. So that will show, that will be our kind of goal to show security for QKD. And if you'd like to read up more upon this of why this is the right definition, there's some nice work to show that this is the right or composable definition. And actually, historically, the first proofs of QKD did not use this. They used something called accessible information, and that was shown to be, what am I trying to say? Oh, yeah, it's shown to be inadequate if you actually want to use the key as a one-time pad. So now we know better, and this is what we aim for. I want to give you, so this is the protocol that we've looked at a high level. And I want to give you more details about each step so that we can know what are the parameters and how you actually do this and how that affects the security. I talked about error correction. So that was, they have this bound on the error rate between Alice and Bob, and then we want to remove the errors so that they agree on the same secret. Yep?
So maybe you said this and I missed it. Basic question. So if row AE is unentangled, it is known that there's no security. That's why you want to look at the trace distance between row AE and the tensor product.
This row AE?
So in the next slide, you know, this trace distance, yeah.
Oh, yeah, sorry.
Here, right?
Yeah.
Trace distance with the row, sorry, XE.
XE, that's right, okay.
Yeah, XE. So XE and the tensor product of mu X and row E.
Mm-hmm.
So it's a known fact that if row XE is a tensor product, then there's no security, and that's why you want to use this measure.
If row XE is in this type of tensor product, then there is security. I'm not sure that there is security. Yes, because they're independent. Okay, independent. So there's two things that this equation summarizes: the independence, which is given by the tensor product, and then the target being mu, which is uniform.
So independence is desired.
Yes. Yes, independence will mean that the E system contains no information about X. Yes. Why is it what?
Why was it in quotes?
Oh, because I don't know any formal way to express no information. I mean, I can talk about entropy, I can talk about all sorts of things, but it's just so blah that I don't know how to prove anything about it. Yeah. Okay, so error correction in more details. Suppose Alice's bit, let's call xi Alice's bit string. So she has x1, x2 up to xn, and Bob b1, b2 up to bn, and these are the outcomes of the measurements after the sifting. From now on, kind of suppose that they chose the same basis. And we could have a whole summer school on error correcting codes. This is some of the basic stuff. My apologies if this is probably going too fast. I don't want to necessarily spend too much time on it. Basically, you can see this as an error correcting problem, and we have techniques to deal with this. She can choose a random code word and send C XOR X to Bob. So this seems to be possibly problematic because this gives some information about X. We'll compensate for that later. And then Bob can decode to the closest code word, so we'll use the properties of the code that they have this decoding property if the noise rate is not too high. And he'll actually manage to reconstruct the correct X given his Y on his side, and that information about U. So short argument shows, using the properties of that this code corrects a small number of errors, then we can actually conclude that Bob gets the correct X. So now we've kind of solved this problem of reconciling the information at the cost, of course, of some classical communication. And we'll compensate once more for this leakage later. For efficiency, actually, we don't need to send this entire U. She can send what's called the syndrome, which is an embodiment of the actual error. Okay, so the syndrome, the important thing to remember is n minus k bits of length, where k is the log of the size of the code, which is the number of code words. Okay, and as I mentioned, we'll compensate for this leakage later. So that's because Eve sees all this communication, this public communication, and gives her information about the final key. Okay, so next I want to tell you about privacy amplification. This is to basically squeeze out Eve. She may have some remaining information from her eavesdropping and from the error correction. Okay, so here's where I get to formalize information, and we'll do that in terms of entropy. Entropy is a measure of uncertainty in a system. It's used all over the place in physics, information theory, cryptography, et cetera. So one of the famous ones is called Shannon entropy of a random variable. For cryptography, min entropy is even more, and Shannon entropy tells you about the uncertainty, kind of like the averaged uncertainty of a system. Min entropy is more relevant for cryptography. And once more, it's more the operational definition that's useful. And it captures how hard it is to guess the value described by a random variable. So if you have a description of a random variable, you know the entire description, and then I'm going to draw from that distribution, and I'm telling you, guess what the outcome is going to be, you will choose the outcome that's most likely. Okay, I'm not, if it's a biased coin, you have no advantage. If it's something that has a peak on a certain x, then you'll guess that x. And that's exactly what the min entropy characterizes, which is the minus log of that maximal probability. So for the adversary, it really makes sense to talk about the adversary's min entropy if it would be Eve's best guess on what's the final key. And we want to make that as uniform as possible, because we want all the keys to have almost the same probability. Conditional min entropy is even more relevant because now there's a side system, like an auxiliary system that is kind of used as a advice or something. So it's the min entropy conditioned on knowing that random variable y. Our final, building up to the final definition that we're going to use is quantum conditional min entropy. I'll just go straight to the operational meaning. We're using it for this classical quantum state, rho xe, and it's the negative log of the success probability of predicting x when using an optimal strategy and having access to the quantum system E. This is very close to the setup that we'll have for QKD, of course, where x is going to be the final key that they'll agree upon. Any questions or comments about min entropy? Okay. Okay, this is repetitive from the previous slide. The point being, of course, that this quantum conditional min entropy, it quantifies how much uncertainty Eve has on a classical X. Privacy amplification, okay, so that's the information-theoretic quantity. Privacy amplification is a method that you apply to a string, a random variable, if you like, and it's going to transform a bound on the conditional min entropy into a uniform key. Actually, even on the quantum conditional min entropy into a uniform key. Okay, so this rho xe doesn't say anything about the uniformity. The key k is computed as a function f. F is the privacy amplification function of s, which is s is a random seed in x. So we're going to add some random seed. We can prove that actually it's required to have this random seed, otherwise the min entropy is not going to help. And what we'll choose is okay, I think this is kind of, it moved around. Just check. Okay, so this is an equation that should be right after to define f. F is a universal hash function if for all x not equal to x, f of s comma x, the probability that f of s comma x is equal to f of s comma x prime is 1 over the size of k. So it's basically, a hash function. And so the idea is that we're going to apply the hash function. That's going to do our privacy amplification. And we'll use known information about the min entropy. How we actually know this is coming up. So say you knew the min entropy of the quantum conditional min entropy, and you applied the hash function f to get the k register. The s register is the seed. So at this point, Eve will also know the seed. And so we'll have the trace distance between this actual thing that we're doing and the ideal thing, which is a random key tensor product with Eve's system. And then we'll be able to bound that to be small, depending on the min entropy that we have. So when we actually go to do this, we'll choose L. L is the size of the output of the of F. Sorry, I should have defined that. Maybe it's hidden here. I don't remember. For L at most, the quantum conditional min entropy, we'll get an L-bit uniform key. So that's what the output here is going to give you. So the main thing that we still need to do is to bound the conditional quantum min entropy. And that's where you have different proof techniques to do that. I mean, some proof techniques don't actually go through these steps, like the error correction version, but most modern ones kind of do. This reference on sampling gives us a way to bound this quantum conditional entropy. For now, let's go back to the classical world and think about a problem that is relatively straightforward. Yeah. Oh, do we require the function to be claw-free for this hash function? I don't know. Is this definition saying that? Is a claw when this happens?
Yeah, like there are two primitives for the same.
Yeah, so I'm saying that the probability that this happens is maximally small, or small.
But that's assuming S is uniform.
Yes. I don't know. Okay, so looking at this classical, relatively simple problem, the Hamming weight of a bit string, this is a basic definition. W of x, it's the sum of all the bits. So namely, it's the number of ones in that bit string. The relative Hamming weight will scale that by the length of the string. So this is a number between 0 and 1. And say we have this problem of, okay, yeah, so, and we'll define the kind of a, we'll say that the Hamming weight, the relative Hamming weight of x is within epsilon of beta if this holds, namely the Hamming weight of x is within epsilon of beta, which is this absolute value notation. So this is a different notation just to say that it's approximately beta. So the problem, the thing that we're looking at is we have this unknown string x, and it's as if you have access to x by looking at certain positions only. And by having access to certain positions only, we'll call this a sample and estimate strategy, which is to choose a random subset of the positions of size linear and m, and look at those ones, compute the relative Hamming weight of the ones that you've opened, and output that as the estimate of the Hamming weight of the, this notation means the complementary string. Okay, so we'll open these white ones, and from that we'll get the estimate, and then we'll output the estimate as the estimate of the relative Hamming weight of the dark ones. Okay, very straightforward. You might wonder why you would ever want to do this. This becomes very relevant coming up, and we'll define the error probability of such a sample and estimate strategy as the maximum of all strings, that the probability that the weight of the complementary string is not within epsilon of the estimate. And some classical conventional inequalities, namely the Hufting inequality, gives you a bound on the success probability on the error probability of such a strategy, right? You know, the more that you open, the more close you'll approximate the actual relative Hamming weight, et cetera. And we actually get a really nice satisfactory bound here. We're going to do something similar, yet quantum sampling. We have an n-qubit quantum system. We'll be choosing a random subset of the qubits, measuring them in the computational basis, and then concluding something. Okay, so even like what could you possibly conclude is something to be defined, right? Like we're not, I don't know, there's no relative Hamming weight necessarily for qubits. We'll solve all these issues with our notation. So given an unknown quantum system, of m qubits, possibly entangled with environment E, consider the strategy of measuring a subset T of the qubits and the computational basis as an estimate of the relative Hamming weight. We'll formalize this shortly. Okay, so same thing, these are qubits, and we'll output the estimate, and then we're like, okay, well, what does that mean about the other ones? If these were all ket zeros, say, and then you measure and you get your relative, your estimate is going to be 0, and yes, indeed, the remaining system is all ket zeros. However, we know that there are superpositions. We know that there, like, general density matrices are not just about, it's not just about Hamming weight. Okay, so what Bouman and Fehr showed is that if the estimation strategy in the classical case has a small error, then it also has a small error in the quantum case. There's like a square root difference. And they also answered this question of what's your target state anyways? Your target state anyways is this. This, which is a superposition with some coefficients. We don't know exactly what the alpha y's are, but we have the ket y's. And the ket y's have a Hamming weight. These are classical strings, so we can talk about their Hamming weight. They have a Hamming weight close to beta, which is your estimate. And then there's a tensor product with an environment that can depend on y. So this is a classical quantum state. No, it's not. This is a quantum state, because it's a superposition. And this register here, we can say a lot about it, namely that it's a superposition of terms with small Hamming weight, or Hamming weight within beta. Okay, and then there's an error term in the Bouman-Fehr, which we'll kind of keep track of, but I'll just call it a small error right now. Okay, maybe you're seeing the link with QKD, maybe not. QKD has this type of sampling flavor because that's when they compare, and they're going to be comparing the positions and aborting if there are too many differences. Kind of similar to this sampling thing, they're kind of estimating the relative Hamming weight of their comparisons. Okay, so that's what we're going to try to massage. We're going to try to massage this theorem into QKD. Right, quantum sampling in QKD. So how could we see QKD as a sampling thing? Okay, we've talked about this notation before. In QKD, Alice and Bob will compare xi with yi. So the logical operation for that would be the XOR. And if the XOR is 0, then they're happy. If the XOR is 1, then they're sad. Then because they don't want too many differences. So we'll define these new random variables, Si, which is the XOR, and Wi, which is a little bit funny. It's Xi if theta I is equal to 0, and Yi if theta I is equal to 1. Okay, so suppose that Alice and Bob were going to do the QKD and furthermore compute these outputs, these random variables, Si and Wi. So they get this larger classical quantum state which includes X, Y, S, W, and E. And the idea is that we're going to do this, we're going to once more transform the protocol. We're going to transform it to a different protocol, easier to analyze. The security of the transform protocol implies security of the initial one. This transformation is not as major as the purification one. So this state here can be obtained differently by applying this unitary defined by Hadamard on the first qubit and B XOR C on the second one, where the input is ket B, ket C. So we'll look at the qubits that Bob and Alice share initially, and we'll apply this joint unitary. Of course, they can't do this in real life. we'll do it on paper. We can't do it in real life because they can't compare, they don't have 2-qubit operations, but we can do this on paper. And this is a different way to obtain the same rho, theta, xy, SWE by first doing this quantum operation and then measuring. And so we'll define doing the quantum operation, then measuring S and W, and from those deducing X and Y as the quantum system sigma. And this is just a different way to obtain the same rho. So these two are identical. And from now on, we'll analyze the sigma. When looking at the sigma, that is really close to sampling and comparing to the system S being 0. Okay, so furthermore, we'll take the basis choice theta as when theta is equal to 0, those are the ones that are opened and compared in the sifting phase, and not in the phase where we estimate the error rate, the beta. That's when theta is equal to 0. When theta is equal to 1, those are the ones that are going to be used for the shared secret key. So we're applying sampling on this subset. It'll be of size n/2 in general, and estimating the Hamming rate, the relative Hamming weight beta, and that's exactly this error rate that we're computing in QKD. By this Bouman-Fehr theorem, the error estimate beta of the relative Hamming weight for the rest of the system, because remember that Bouman-Fehr tells us that if you estimate on some part of the system, you can actually get some confidence on the rest of the system. So that means that from their initial error estimate, they're actually getting an idea of what are the qubits that they did not measure. And that's important. Hence, they are close to what was out in this theorem, which was the superposition of classical strings Z, where each Z has Hamming weight approximately beta. And then tensor product with some reference system that Eve has. These qubits, which I repeat are not measured, yet by the sampling we have an idea of what they are, they're going to be measured, at this point they're not measured, they're going to be measured next in the Hadamard basis. So if you have something, it turns out that if you have a state like this, okay, a really simple case is, say, beta is equal to 0. Then you should have actually something close to the Ket 0 state. And you measure all of those in the Hadamard basis, you'll get uniform randomness. And it turns out that if you're even a little bit fuzzy, like the beta is a little, maybe up to 11%, then you have this superposition, and then you measure, you'll still get uniform randomness, or approximate uniform randomness. And that's what this theorem should show, this lemma. Okay, so we're close to this one, and this lemma says that if you're close to this, and that this Z has a Hamming has a relative Hamming weight that is small, then you can bound the min entropy of W obtained by measuring in the Hadamard basis, and that would be this W random variable, to be at least this. So you have this lower bound on the min entropy created, the quantum conditional min entropy of W. This H is this well-known entropy, binary entropy. So that is that's the bound that we're going to use into the privacy amplification. We still need to compensate for the further classical information that Eve gets, and that happens when we do the error correction, as well as the choosing of the about the error correction. So it remains to compensate for that, and there's this thing called the chain rule that says that if you reveal n bits of information in terms of length of a message, then that reduces the min entropy according to the same number of bits. So if you do that calculation and remove, I think it was called n minus k in the error correction step, and clean everything up, then you'll have this min entropy bound on the final key that Alice and Bob agree upon. And then we'll apply privacy amplification with these parameters, and that gives you the length of the final key that you can get. And we know that it'll be close in trace distance to a uniform key that's in tensor product with whatever Eve has. Okay, so that's a mouthful. It's a lot of steps in QKD. I hope it gives you an idea of one way that we can show security and an appreciation that these things are still rather complex as far as we understand them.